All right, section 4.3, we're going to take a look at arithmetic in our system. Our system, right? Okay. So one of the things that you have seen before, but you might not have thought about it from this perspective, is something called expanded form. So expanded form is a form in which the value of the digits in each position is made clear. So when we write 942, we don't say 942, right? My daughter that just arrived from Ethiopia keeps saying 942 because she doesn't understand the place value words that we use quite yet. So she says 942, but we don't say that. We say 900, and then we say 42, and the word 40 means 4 tens. So it's 9 hundreds, 4 tens, and 2 ones. Okay, so it's associating the place value along with the number that's in that value. And in particular, we can also write it that way. So we can actually write it as, whoops, wrong color, 9 hundreds, so like 9 times 100. We can write it as 4 times 10, and then 2 times 1. And what happens is that you start to recognize, if we wrote out enough of them anyway, you'd see that all of these numbers right here are our base 10 system coming to play. So when we worked with the Babylonians, you did a base 60 system. So we talked about the fact that it was 60 and 60 squared and 60 cubed. The Mayans was this modified base 20 where we saw some powers of 20 coming about. Well, these are all powers of 10. So what we can actually express this as is 10 squared, 10 to the first. And as awkward as it feels, this is the same as 10 to the 0. Now, the power itself also, if you notice, actually mimics the number of zeros that are in the number. So it's a good reminder, well, what power is it? Well, how many zeros do you have? 4 zeros? Well, then it's the power 4. 6 zeros? It's the power 6. Okay? So we're going to do this for some different numbers. So the first number that we have is 12,398. So we're going to take each individual digit and we're going to multiply it by the place value that it's in. So 1 is in what place? Well, the 10,000s place. Now, do you have to write this step out? Well, no, not necessarily, but if you're sort of struggling with how do I start, this is a good place to start. It's in the 10,000s place. How about the 2? Yep, 1,000s place. Then we have a 3, hundreds place. A 9 is in the tens place, and then the last one is an 8, and it's in the ones place. So this is breaking it down by place value, and then we can actually count the zeros to figure out what the powers of 10 are that we have for each of them. So this first one is 1 times 10 to what power? 4, because there's 4 zeros. And then I have 2 times 10 to what power? 3. And then 3 times 10 squared. 9 times 10 to the 1. That one's maybe the most awkward feeling one, at least until we get to the 0, right? The power of 0. So 9 times 10 to the 1, and then 8 times 10 to the 0. There are 0 zeros in the number 1. So we want to be able to go this direction. We also want to be able to take this number and go back the other direction. Now, if you need that intermediate step as well to write out what this value is, feel free to do so. I'll do it this time. But if you don't need it and you can just go to the next part, that's fine. Do be careful because you want to make sure that you're seeing that all the powers are here, but some of them have a 0 in that place value. See how they're doing that? They're trying to not mess you up and think, oh, I just skipped over it, and so I'm going to sort of squoosh them together. We have a 0 and we use it well. So if we want to think about this as 5 times 10, so this is a 0. This has to have 5 zeros. There's 2, 3, 4, 5. So this is 100,000. We have a 0, and then there's 4 zeros. 1, 2, 3, 4. That's 10,000. We have a 3 with 3 zeros. That's 1,000. We have a 5, and then the 10 with 2 zeros is 100. A 6 with just a 10, and then an 8 with a 1. So this is sort of going in reverse. Because they've represented the 0 piece here, we're not skipping any place values, and so the numbers actually read straight off. This is 5, 0, 3, 5, 6, 8. that. And you can check to make sure, is the 5 in the 100,000ths place? Yes. Is the 0 in the 10,000ths place? Yes. And you can go down the line to make sure they're right in the right place value as you go. Any questions about that? Okay, the next thing we're going to look at is going to feel like it's oddly placed, like why did it show up right here? But I'll show you why after the next example. It's a distributive property. It sort of feels like an odd throw-in at the moment. The distributive property talks about how we are able to, and we usually think it from going this direction over here, right? So I take the number A and I multiply it by the B and I multiply it by the C. That's usually the direction we go as we talk about multiplying through. We're actually having it written the other way, and you'll see why when we get to our example. But it doesn't matter. An equality means that I can go from left to right or from right to left. It doesn't make any difference. So the distributive property that you're seeing here is written almost like it's factoring. It's noticing that there's an A that's multiplied by both of them, and then I'm pulling the A back out and writing the B and the C added together. So this comes into play because what we're going to be looking at is what the addition looks like if we write our addition in expanded form. And one of the reference points you can have that I think is a really pretty good one is money. Our base system works really well with our dollar bills. Now, we can't use the dollar bill that's a 5 for this to make sense, and the 20. But if you think about our ones dollar bill, right, our single bill, your tens bill, our hundreds bill, those kinds of bills. We don't have a thousands bill, but you can imagine that kind of a process and this kind of idea that we're going to be doing with this regrouping. So this one says to add or subtract in expanded form. Expanded form means writing each of these in its place value. In other words, instead of writing 75, we're writing 7 times 10 plus 5 times 1. Or more specifically, right, what we just did a moment ago, 7 times 10 to the first and 5 times 10 to the 0. So we're writing each of them out in this expanded form notation. I'm not going to write any more in this form. I'm going to jump straight over to the one on the right. If you need to see the one on the left, just write it down for yourself. That's okay. The next one is supposed to be 34, so it's 3 times 10 to the first plus 4 times 10 to the 0. And we're told to add these together. Now, when I'm adding these together, it's very much using the distributive property. We're saying that each of these that are saying times 10 to the 0 are being multiplied like by the same value A. The 10 to the 0 is an A, and therefore, since they're both being multiplied by 10 to the 0, I can add the 4 and the 5 together because they are both being multiplied by the same thing. That's what's allowing this to work, is the distributive property. So we're going to work just like we would with arithmetic. You know, back in the day, you're going to start on the right-hand side, you're going to move left, which is sort of counterintuitive to how we read. But we can do that. So we've got a 9 here, and it's still times 10 to the 0. That's the distributive property. But weird things happen with the next one because the number becomes a 2-digit number. 7 plus 3 is actually 10. Now, there's nothing wrong with it being a 10, except that it's 2 digits. And if you think about this again in a money sense, and you had 10 tens, you might be just a little annoyed to have 10 tens, right? You might spend 10 tens quicker than you might spend the corresponding larger bill that goes with them, because it's easier to spend 10 tens. But 10 tens is the same as 100. It's a $100 bill, right? So what we see happening here is we see the need for us to change this into something bigger. This piece actually becomes 1/100. Well, 100 is 10 squared. I don't have any tens left over when I do that exchange, so it's 0 tens. And then I have my 9 ones, or 10 to the 0s. So I'm exchanging, right? I'm exchanging 10 tens for a 100. And 100 is written as 10 squared. And when I do that exchange, the corresponding numbers that are written here at the bottom now, this 1, this 0, and this 9, are the single digits if I write it back in the standard form instead of my expanded form. So this is the number 109. And the expanded form looks like this. So what does this look like when you get into my math lab? Well, it doesn't look like multiple choice, and it doesn't look like you can actually start at 75 plus 34 and simply write 109. they're going to have blanks for you to fill in with this kind of a scaffolding for you're putting the numbers in the right place of where they're supposed to go. That's what it's going to look like. All right, so it's going to look very much like what I have with some blank spots, in there, kind of like when they drew the Venn diagrams finally, and they had those blank spots in there, and you had to fill them in. It's going to look like that. All right, any questions on this? So we're going to do a subtraction one next. Let me scoot this up. Okay, so we're going to do the same thing with subtraction. We have 7 times 10 to the first, and 4 times 10 to the 0. And then we're supposed to subtract the 48. Well, that means I subtract a 40 and I subtract an 8. So I need to subtract 4 tens, so 4 times 10 to the first, and I need to subtract 8 ones, 8 times 10 to the 0. Now that's a problem. At least the way it's currently set up. What's the problem? Yeah, there's not enough, right? Like if I'm working from the right to the left like I do with addition, there's not enough to take 8 away from 4. Correct? So what we have done and you've done in the past is something either called borrowing or regrouping, depending on the curriculum that you've used. Regrouping is a more current word that people like to use for some reason, just so you know. But borrowing is the one that I grew up with, and some of you are like, yep, that's what I've heard too. Either one's fine. But what we're actually doing is we are taking the number 7, right? It's 7 $10 bills, and I'm taking one of those $10 bills and I'm taking it over to somebody who has change, right? And I'm turning, if I only have tens and ones, one of the 7 $10 bills, one of my $10 bills, into what? Okay, well, I'm turning it into 10 ones, right? And I already have the 4 ones, so it becomes 14 ones. So my 7 $10 bills is now 6 $10 bills. And I take those 10 single dollar bills plus the 4 single dollar bills that I originally had, and now I have 14 single dollar bills. Can you picture you doing it in your mind? Have you ever exchanged money like that before? My children do it all the time at church when they want to buy something back in the teen room for, snacks. They go and they take money and they exchange it, and they're supposed to bring the money back to me. They usually do. Okay, so what happens? Well, now I'm able to do the subtraction, right? Now I can actually do the 14 minus 8. So 14 minus 8 is 6. So now I have 6 ones, which is 6 10 to the zeros. And it's addition, right? Because I've done my subtraction to eliminate the negative. And now I have 6 tens minus 4 tens, and I get back 2 tens. So 2 times 10 to the 1. And then once again, like on the last time, the numbers at the beginning are the final value in standard form, 26. Now, can you check this on your calculator or just with standard form subtraction? Well, of course you can, and you should, right? And that way, if you find out that you did this and at the end you get 26, like you're supposed to get it, in your calculator it tells you that, or on by hand you did that, and you go back over here and it says something else, you've made an error, right? Now you got to figure out where the error was and you can fix it. So there's always the ability to check your work when you're working with expanded form. All right. The next thing we're going to take a look at is an old-fashioned calculator. The earliest calculator is called an abacus. So this was a method used for speed calculating. We're not going to go into the full extent of all the things. We're just going to dabble in it just a little bit. But there's an example here at the bottom of an abacus. This is what one would look like. This does not look like the toy abacus that my children had when they were little. It had 10 beads on each strand and all this kind of stuff. It doesn't look like that. So this is like legit the kind of ones they would have used. Each of the prongs actually represents a power of 10. Okay, so you've got 10 to the 0 on the right, all the way over to 10 to the 4 on the left. We move beads. There's only one bead above this horizontal breaking point, right? It's either at the top or it's towards the middle. And there are 4 beads that are below. Okay? The beads that are above the rod, the horizontal rod, are worth 5. The beads that are below the horizontal rod are worth 1. Okay? So each one of these beads down here is worth 1. So 1, 1, 1, 1. These beads are each worth 5, 5, 5, and so forth. If the numbers are pushed toward the middle, they're active. If the numbers are pushed away, it's like they're not really there. They're there because this is a physical object. I don't just take the beads off. Like, that's not a thing. But we have to be able to say which ones apply and we're using and which ones we're not using. So we're using them if they're pushed towards the middle, and we're not using them if we're pushed away. So in this picture, all the beads that are sort of in black colored, those are active beads right now. And all the beads that are pushed away, that are put in blue to distinguish them, are non-active beads. They're just there because I can't physically remove them from the object. Okay, everybody good so far? So taking a look at these beads, I want us to just write down for the moment what value each one holds. And it doesn't matter if I go left to right or right to left. So we're just going to go from left to right, the way we would read. So on this one, I have 3 beads below that are active, and I have no beads above that are, correct? This represents the number 3. 3 active beads from below, no active beads from above. So this is the number 3. So I'm going to just put a 3 down here for now. How about on the next one? What do you think this number represents? This is 1. There's 1 active bead from the bottom pushed toward the middle. That's it. So I've got a 1. How about over here, the third one? 7. Why is it 7? Yeah, the one that's above the line's worth 5. Yeah? And then the 2 that are below the line are each worth 1. So I have 5 from above, 2 from below. I have a total of 7. How about the next one? That's 0, right? There is nothing pushed toward the middle. So that is a 0. And how about my last one? That one's 6. So the way that this is currently displayed on this abacus, this is the number 31,706. Does that make sense? Okay. So what we're going to do is we're going to start out with a number, and we're going to start with a picture. Yeah, that's the first one I'm going to do. We're going to do a picture, and we're going to figure out what the number is, kind of like I did on this one. Okay. And then we're going to start a number, and we're going to start with a number, and we're going to create the picture. All good? Okay. So I need to give you a second to draw it, so I will stay quiet and let you draw the picture that's going on here. The colors are really irrelevant. They're just for illustrative purposes. Obviously, the beads themselves are one solid color. They don't change in a physical, like abacus form. So just draw them hollow, draw them filled in. You don't need to worry about the color of them. When you get done drawing it, go ahead and do your best to try and figure out what each of the rods represents, moving from left to right. Write down the number like we did on the last example. What's the first rod? 1. What's the second rod? 0. The third one? 2. And the next one? 5. And the last one? 6. So this is the number 10,256. What do you think? It's okay. It's not bad, right? Okay. We're going to do the opposite now, right? We keep doing everything in forward and reverse, right? We're going to keep going back and forth. So this one is the number 70,163. We're going to draw the abacus that would represent this value. So Yours will probably be straighter than mine. We'll see. Okay. So how do I get a number 7 at the very beginning? First of all, you should have 5 prongs because we have 5 numbers. 1, 2, 3, 4, 5. So I have 5. How do you get the number 7? Got to have a top one down. And I need 2 of the bottom ones up, right? All right, those are too thick. Let's try one more time. That's not too bad. All right. Now, it's not going to matter because you're doing it in an electronic system that's going to force it to happen. But if you were doing this on paper and you did just this, you'd be missing some beads because you can't really take the beads off. There are still 2 beads that I need to draw. Where are they? Yeah, they're down at the bottom of this. So when you get to doing this inside of my math lab, you're going to be looking for multiple choice kind of questions. They're not going to physically have you move beads. Maybe sometime. That would be really actually a pretty cool thing if they could physically shift the beads around on an abacus. So there are 2 more beads. They're down here at the bottom. So make sure you put the other 2 missing beads down here at the bottom. Okay. How about the number 0? None in the middle. So there is still a bead that's going on above my line, so it has to be pushed away to the top. And then what about below the line? Yeah, 4 along the bottom. So I've got 1, 2, 3, whoops.
Does it have to be that way? Like, could you not split it up to 2 or 3 or something?
So this is a physical object, remember? Okay, so since it's a physical object, there are 4 beads that are always beneath that rod, and there is 1 bead that's always above it. So all I can do is to shift it up and down. I can shift it away from the middle, or I can shift it towards the middle, and those are my only choices. So I can't split something any differently. Yeah. Next number is 1. How do I get the number 1 on my next rod? 1 from below, right? So I have this piece right here, and then the 1 from above would be pushed away, and the 3 would be below. I can't seem to center mine today. That's not bad. We'll go with it. All right. The next number is a 6. 1 on top and 1 below. So here's 1 on top. Here's 1 below. And then what else do I need? 3 more on the bottom, right? Last number is a 6. Wait, that was supposed to be 6. I'm sorry, I probably said it wrong. Oh, that's not what I wanted. Try one more time. All right, this was supposed to be 5, right? Oh, 6. Oh, I was looking at my paper for the problem above. Sorry, 3 is what we're on now. So sorry, 3. How do we get the number 3? 3 below need to be pushed up to the middle. So here's 1, 2, and 3. And I've got some missing. What do I need? 1 bead at the bottom and 1 bead at the very top. Like this. Is that okay? Okay, last topic in this section. And so those of you who are maybe education majors will see this again when you take number theory class we offer here. If you work in the schools at any point, or if you have young children either in your family or when you have young children, you will see this again. And you're going to be like, oh, she told me about that thing. So this is called lattice multiplication. Lattice multiplication is a method for finding products. Okay? So what we do is we create rows and columns for our digits. We divide each box along the diagonal. We compute each single digit product with the tens digit in the top left, the ones digit in the bottom right, and then we add along diagonals. So jot those details down, and then I'll show you what it does. Okay, so this is for multiplication with multi-digit numbers. So 2 digits by 2 digits, 2 by 3, 3 by 3, anything bigger than 1 by 1 digits, okay? If you think back to when you learned how to multiply with 2-digit numbers, let me just run through real quick. We usually put the number on top as the larger one. And one of the things that happens is that you start on the right-hand side, and you multiply, and you say, okay, 3 times 7 is 21, right? And in the middle of this, you carry the 2 to the top. And then you say 3 times 8 is 24. And then in the middle of multiplying, you add, which is a little awkward, right? You were just multiplying, and now you're changing operations. So we have 26. And we do it again, right? We have 3 times 1 is 3, and in the middle of multiplying, we add the 2 on the top, and then we get a 5. And then this mysterious 0 shows up. And if I had to ask you why, many of you probably don't know why it shows up. The reason it shows up is because I'm about to multiply by the 2, but the 2 is in the tens place, which means I'm not really multiplying by 2, I'm multiplying by 20. That's why the 0 is showing up, okay? So I don't really need to finish multiplying the problem out, but what I want to point out to you is that in the middle of multiplying, we're doing multiple things. We're multiplying, and we're adding, and we're throwing in a 0, and then at the very end, we add it all together. And so we've got sort of a mix mash of all these different operations happening at one time. And if you're learning this for the very first time, that's a lot. And in fact, when my daughter Abby was learning this for the first time in 3rd grade, and Abby is a very bright young lady, that was really hard for her to separate all those operations at the same time. And interestingly enough, I had been teaching a number of courses at the time, and I knew about the lattice method. I showed her this, and she loved it. So does she use the lattice method now? Well, of course not, because as you see in a minute here, you're going to see that it's a lot of writing. And so it's not very condensed. But it isolates operations really well. Okay, so here's the way the lattice operations, or lattice method works. Because I have the number that's a 3-digit number, it doesn't matter if I put it on the top or on the left, or I'm sorry, the top or on the right. I'm just going to put my 3-digit number, 187, along the top. And then I'm going to put my other number, which was 23, along the right-hand side. And I'm going to draw a 3 by 2 box. So it's going to be 2 long because of a 2-digit number here, and it's going to be 3 columns wide because of 3 columns there. If you had done the 23 on the top and the 187 on the side, it would simply be 2 columns wide and 3 columns long. It doesn't make any difference. And then what we're going to do is we're going to split each of these boxes diagonally. Okay, so far so good? And we're going to do a bunch of single-digit multiplications. So single-digit multiplications are very nice. So when I multiply 1 times 2, and it doesn't matter where I start. I can start in any box I want. I'm just going to work from left to right because I'm like that. Okay, so we're going to do 1 times 2, and that's the number 2, of course. And I'm going to put the 2 right here. So I'm in the same row and column as I multiplied from. And if it's a single digit number, it goes in the bottom right-hand corner. Now notice when I multiply 8 times 2, I get 16. So I put the 1 on top and the 6 on bottom. So there's my 16. So top corner is the tens digit, the bottom corner is the ones digit. And we're going to do each box like this. 7 times 2 is 14. Down here I've got 1 times 3, 3. I have 8 times 3, 24. And then I have 7 times 3, 21. So again, what's going to happen in my math lab is they're going to give you this grid, and you're going to fill in all the numbers in the right places. That's what you're going to do. The last thing that it tells you to do is you're going to add along the diagonals. So these diagonals are actually going to extend now. And you have to start in the bottom right-hand corner. All these numbers on the outside, we're done with them. We've used them to do the multiplication. We are only adding the numbers inside the box. Okay? So in the bottom right-hand corner, it's a 1. And the next diagonal, I have 4 plus 2 plus 4, which is 10. So I've got a 0 down here, and I'm carrying my 1 to the next column, which is why I'm using colors, because I want you to see where they're all going. Now I have 1 plus 1 plus 6 plus 2 plus 3. 13 is right, yes. So we got a 3 down here, and we carry the 1. And I have 1 plus 1 plus 2, which is 4. So we do all the multiplication first, and we do all the addition at the end. And that's really what lattice multiplication is good for, separating our operations. Do you have to like it? No, you don't. I'm just showing you another method for multiplication, because maybe you too will have a child someday who will not understand the standard multiplication method, or their teacher will simply send this home, and you're not going to be blindsided now when that nephew or niece or child or brother or sister of yours comes home with this, and you're like, I don't know what they're talking about, right? Now you're going to know what they're talking about. So the answer is along the bottom, 4301. This is 4,301. Okay, so we're going to do another example, and I'll let you give it a try, and then we'll come back together to make sure everybody's good. This is a 3 by 3 number. It's 912 by 483. So how big is my grid going to be? A 3 by 3 grid, right? 3 columns, 3 rows. So the setup will actually be a larger setup than the previous one we had. 3 columns and 3 rows. And maybe yours will actually be a little bit more balanced than mine, but maybe not. All right, we'll go with it. So it doesn't matter where you put it. I'm just going to do them in order. 912 on top, 483 on the right. Okay, so go ahead, fill in your grid, and then add along your diagonals, and we're going to check to make sure everybody has the same result at the end. All right, real quick, you're going to lead me through your diagram. Let's go just straight across the top. What are the numbers in my boxes? 36, You did yours the other direction? 4, okay. Oh, I see what you're saying. You carried a 1. And then 8. Next row. 27. What's next? 3 and 6. Okay. Did you extend your diagonals? Good. Lots of diagonals to extend. Looks like I have 6 down here. 6 plus 3 is 9. 8 plus 1 plus 8 plus 7. 24? I'm using the same color now. Sorry. I'm carrying it too. I should have changed colors. I didn't. All right, so I have this 2 that I brought up. 2, 4, 2, 4, 2, 2. 10. So there's a 0, and I'm going to bring another 1. And then I have 1, 6, and 7. 14, carry 1, and 4. So my answer is 440496. Okay, any questions?